My name is Dragan Nešić, and I will chair this plenary presented by Anna Stefanopoulou, and it will be co-chaired by Maria Elena Walker. Let me just first say that I'm really pleased to see Anna present this plenary. I met Anna when I was PhD, well, postdoc, just finished my PhD in Santa Barbara. She was a young faculty, and she just went to Michigan from Santa Barbara and just went from one strength to another. So she's currently William Clay Ford Professor of Manufacturing at University of Michigan. She has held a number of prominent positions and received a number of awards. I would just mention that she's a member, she's a fellow of IEEE and of ASME. And she actually told me that she feels at home at Melbourne because it has such a big Greek community here, and it's surrounded by water. And an interesting fact about Anna is that she's a very versatile engineer. She studied naval marine engineering in Athens, and then she moved to electrical engineering during her PhD. Now she teaches mechanical engineers, and she would actually talk about chemical engineering. So I would like to invite Anna to the stage, so please welcome Anna.
Thanks. Thank you very much. What a blaze. Wow. Okay. So I have a loud voice. Maybe you can turn down the volume a little bit, right? Okay. Miroslav said I'm following a Greek heritage, the unsung heroes of battery technology. I think that sounds also very Greek. Thank you very much to the organizing committee for inviting me, and thank you very much for bringing the CDC at Melbourne. What a great city. I have never been before here. Okay, so I have 47 slides. Hopefully it will work out. So how do they say, buckle up and stay calm? So I think in this chart here, I will I'll use this chart. This is the energy storage versus power source. Any kind of storages. So you see here the batteries, the flywheels, the capacitors, and there is an important aspect that a lot of people are worrying about and how to use them, especially with using large energy storage for renewables, which is so important. But I'm using actually this graph to tell you what I will not discuss today and not actually what I will discuss. So I will just focus on lithium-ion batteries. As you can see in the chart, there is an area with batteries, and I will be talking about lithium-ion batteries. And let's see if this works. This chart has some units that for us, even that we're good engineers, we actually cannot relate very well. It's actually specific energy and specific power, so I'll give you something that you can relate to. 1 mile travel from a vehicle, you need something like 100 grams of gasoline, a little bit less of natural gas. Of course, you will have to account for more weight for the storage. It is loud. Okay. And then just to give you an idea, okay, maybe I need to be closer. Okay, I'll be kind of back here. You see also what kind of, the same amount of energy, you need actually quite a bit of lead acid. That's why we moved to lithium ion. And what I will be comparing, of course, so everybody in our mind, because it knows that maybe you know that I work a lot in fuel cells also. This is the compressed hydrogen, the energy, the weight for the same amount of energy. I will be talking about, okay, I'll find the right spot and I'll stay there. No, okay, I'll do it like this. And then I'll do this. Okay, so lithium-ion batteries, this is what I will focus, and they're high performance, high maintenance, like a lot of good people and very effective people, and I actually say that batteries are like humans. They bleed when you poke them and burst, actually in flames. They hate to be overworked. They're picky about temperature and pressure. I'm definitely like that, especially with a little bit of cold, as you can see. And they're, of course, fuzzy about external pressure, diverse because they come in all kind of packaging format. And yeah, they all will die. So what do we do about our sensitive devices and quite powerful? We need to take care of them. So we're talking about the battery management system. We need the state estimation. The state estimation includes state of charge. Then it includes also the state of health. So how the parameters are aging and drifting and changing over time in a model, let's say. State of power, how fast you can actually draw the amount of energy that you have stored. I will, as you can see, I have grayed out the cell-to-cell balancing. There's not enough time and fast charging type of work that a lot of other also people have worked on. I'll touch upon thermal management. Temperature is very important. Batteries are extremely sensitive to temperature. And I will get into stress management. Speaking about stress, again, talking to this big audience. Okay, so this is the plan. I will spend a few slides describing the lithium-ion principle and the lithium-ion battery energy storage problem. So what you see on the top is the classical wound cell. This is actually what we call, okay. Right. This is what we call a battery. Now, the battery is basically a roll, or kind of a toilet roll. So it has many, many layers of these continuous layers of actually small cells of batteries or layers, strips of batteries. And so what you see here is on the kind of red, around the red area, the yellow stripes are actually the anodes. The anodes are made out of carbon, so you can see the carbon particles. And then we have then the separator, the lithium, moves from the cathode to the anode through the separator, and the cathode is typically a metal oxide. I'm showing you here an iron phosphate type of oxide. Okay. I can show you perhaps also in the chemical reaction because it is telling. So what you do is you have this lithiated metal oxide, and that one splits out lithium and electrons, and then basically the lithium and the electrons are moving to the other side on the anode side and then get embedded inside the carbon, and that's what we call as battery being charged, when the lithium is actually going to the carbon. So let's focus in that unit cell. And my simple explanation for a battery sometimes is two jars that you fill up and you move the lithium from one jar to the other. So the anode and the cathode are just two nice little jars. It's a closed system, so you can actually make your jar lay down to its back. So let's flip it and make it go flat so that we can actually also understand what kind of measurement we actually see, because unfortunately we cannot see, it's not a glass jar, so we cannot see actually the volume in its electrode, so we actually don't know the state of charge and what's energy left. So here is the first, as we saw, the first chemical reaction, and what you see is the iron phosphate get delithiated. As it gets delithiated, notice that it becomes less and less similar to lithium, so its voltage increases. The potential is always against lithium metal, and so that's why, because it's delithiated, its potential increases. On the other side, at the same time, the lithium is embedding itself in the carbon, and so the voltage now for the carbon goes down because it becomes more and more like a lithium. And so what you actually measure when we measure terminal voltage is the difference between these two potentials. Okay? So it's the difference between the two potentials. And you can see that because actually the anode has very small values, it's almost like the cathode. What we do is we actually operate the battery between a certain range because we don't want it to go really low or have the carbon be full of lithium. Whenever it's full of lithium, then actually what happens is that very low potentials in the anode, you can actually have the lithium create plating like metal and dendrites and create sorts that actually go across the separator and sort the cell. So you don't want to operate there, and that's why you actually bound your state of charge away from that region, and therefore you have this system where you operate, you define as zero state of charge and 100% on a safe, let me find this then. You've defined the empty and the full depending actually on your voltage. Okay, so what we have is a very simple model. The model is what we call state. The state actually is just Coulomb counting. It's just an integrator. It keeps track of the current that you're drawing. And it's a Z dot, just an integrator normalized by the capacity of the cell. So very simple. This is what we measure. That's the output. That's the terminal voltage. Or what we call open circuit voltage. So when you don't draw current and you're at steady state, then this is what you would measure. And you can see that sometimes you can use very simple, well, relatively simple nonlinearities to fit your data and get your output nonlinearity. Well, obviously, you don't operate always at rest. You actually draw current constantly. So when you want to use the voltage to actually figure out the state of charge, but that would be under current excitation and transient current. And so what you can see here is basically when I do a pulse in the current, this is what the voltage, this is how the voltage changes. So the voltage, you can see an abrupt drop in the voltage. The abrupt drop is because of a resistance. So it's like the IR drop when you take current. And then what you see is this a little bit of dynamics is what we call diffusion dynamics as the lithium intercalates inside, embeds itself inside the material, the carbon typically. It has diffusion. Think about it as a sponge, so it takes time to soak up the water. Remember again our jars full of liquid. So this is what's going on, and I can model this in a very simplistic way with an RC circuit, and that will be my overpotential. I can add this equation, and now my terminal voltage is the open circuit minus the overpotential minus the IR. Very nice and simple. I am ready to go. In fact, people can actually add more RCs and make it much more higher fidelity in a sense and match really good data, the data with the model. And then it looks like a linear system with an output nonlinearity. Some of these parameters, these RC's parameters, are temperature dependent. So far we talked about the electrical side, so there will be actually connection with the thermal. And okay, we are ready to do our very simple first state of charge estimation. We have a model. We measure voltage. We want to know the internal state. As all estimation problems, it's like an inversion problem, like Professor Goodwin said yesterday. So basically, what is the state of charge that gives us this terminal voltage? That's the solution or the inverse problem. What we do is typically we apply the Coulomb counting. We actually estimate the voltage. We compare it with the measured voltage. We create the error, and the error drives our Coulomb counting to a better value, to the correct value. So this is our way of doing the inversion. And actually, maybe I should say, a very simple model of Kalman filtering for this type of problem was first appeared, maybe there are even before that, in 2002 by Plett, and 638 papers on Kalman filtering on state of charge estimation since then. Just for fun, I did a Scopus search. This is a keyword on a title or keyword of state of charge estimation. So you can see the first graph shows the documents, and the second graph shows the citations. Pretty amazing, right? You can see the growth in the work and the body of work, and in fact, it reached at some point 100 papers per year. And with respect to AIDS index, sounds like a good topic to work on, right, for all of us. Okay, let me dive in a little bit more, again staying on a very simple, with very simple dynamics, very simple model. And so you know, what is the big problem? And it's the classical estimation problem because, let's analyze it a little bit to show you the classical part, I guess. Let's take the voltage and simplify it through a piecewise linear function. So it looks like this. So our voltage equation now is basically V naught with the intersect and then alpha Z, so just the slope, minus IR. Okay, so when I have this very simple model, our estimation is basically I'm starting with an unknown state of charge. I have the same model like my physics. However, you can see that I have a Q hat and an R hat because these are the parameters of my model. And even if I'm not, even if I am a good modeler and I actually have very good parameters in the lab, this, entity will actually degrade, it will age, so the Q and the R will change. The R changes because of aging. Many reasons, many physical reasons. Interface layers grows, delamination between the particles and the layers, pore collapse inside this electrode, and then you have the, you have errors in capacity. So I have a Q hat in my equations. Okay, so in the Q hat in the equations, again, is for similar reasons, particle cracking, and again, different type of layer, interface layer that eats up the lithium and irreversible plating. So having this, taking this into account, then I can compute the estimation error. Here you see my gain L, of course. It drives my dynamics really fast to the right value. Unfortunately, it multiplies the noise. All the good stuff we know, and then we have modeling error. A thing to notice is how this alpha, the role of the alpha. So you have, if you have a very flat voltage behavior with respect to SOC, of course, you can apply high gain. You only can apply high gain. Unfortunately, this alpha affects your convergence rate. And it's kind of, you can see in the picture clearly that if you have such a flat voltage curve, then obviously you have no clue what your state of charge is because basically there's no observability also. You can swing really a lot in state of charge and the voltage measurement you get is exactly the same. Okay, very good. So we know now the problem. We actually would prefer to have a chemistry that will have more steep voltage characteristic with respect to SOC. And then if I look at the steady state for my error at the average steady state error, then you can see how the modeling error in the capacity and the resistance is affecting me. And you can see again the alpha in the denominator. So if the alpha is small, again, you're actually magnifying, in a sense, the modeling errors. Well, so it is a hard problem, right? It's like almost like a quintessential problem that you would actually use in your homework, if you teach estimation. Obviously, in our field, we know that if we have a high sensitivity on some parameters, you do joint estimation of parameters and states, and this is what, of course, we would try to do. The issue here is that, how much data do you have to be able to actually do the states and the parameter estimation? One can apply the Kramer-Rao bounds and using the Fisher information matrix to actually find a bound for the error in state of charge. Again, high voltage noise, it hurts us, and an alpha that is steep will help us, like we said before. How do we do with respect to the parameter, this capacity? Well, this capacity, it's the same problem with the state of charge, but it also has this other square root of the change in SOC. So let's understand a little bit this part. So this is the SOC variation. So it says that if you are on a hybrid vehicle, in a hybrid vehicle, you actually don't use all your SOC. what you do is you operate in actually a very narrow range of SOC. So if you are operating over there, then you clearly have no clue what is your capacity, as you perhaps could be aging. These are the practical problems that industry faces. If you are a risk-adverse owner of a battery all-electric vehicle, and you operate only at the first leg, in fact, you don't completely charge because most of the time you're on the go all the time, but you're risk adverse, so you don't discharge, again, you have the same problem. And of course, for an all-electric vehicle, it's very important to know the capacity, because otherwise you might end up occasionally go to what we call the shoulder. So it's kind of like a shoulder and a neck. That's how they call actually this curve in industry. And so actually if you're on the shoulder, then you actually don't know your capacity and you'll end up stranded. Okay. So far I talked I was in a very linear world, piecewise linear systems. So what I want to highlight is that, of course, when you embrace nonlinearities, you get much more information. Here is an example. This is actually very fresh work submitted to ACC 2018. Hopefully you will get to see it. But what it shows is, in the right-hand side of the graph, it has actually a very small window of data. Let's say you actually have very small amount of data, and you operate at this nonlinear voltage curve. It actually shows the bottom graph on the right. It shows the condition number, and it actually shows that actually if you operate in the transitions between the various linearities, then you actually get a lot of observability. Your condition number becomes actually very low, so you can actually not only estimate the capacity of the cell, you can actually estimate the capacity of each electrode by using nonlinearity. So it's really neat. And you'll say, oh, and why do I care about the capacity of each electrode? Well, the fact is that when the system degrades, the two jars are actually sliding with respect to each other. The two actually capacities of the one electrode and the other, they're not degrading at the same rate. Depending on how you're using the battery, you can be degrading the anode or the cathode, and also depending on the material, you can be degrading differently. So in fact, when you impose a regular capacity estimation, then you can be actually enforcing the voltage limits. But as this graph to the left shows, if you have an aged cell that only the anode, for example, aged, then actually you are still operating in a condition that the anode hurts itself. You can see that the line, the red line at the lower left column figure, it's actually already operating where it actually creates dendrites and plating. So it's actually really important to embrace nonlinearities, and to also, when you do parametric estimation, to actually have the right structure. Professor Goodwin said that yesterday too. I'm amazed, I'm a big fan of his. So he was saying that when you actually do parameter estimation, you have to put the right structure so that the parameters are real physical parameters, that they really age, and then you actually sense the aging in a structured way. So therefore, we move into much more complicated models, and this is where actually the majority of the papers in the last 2-3 years have been focusing on. It's the so-called electrochemical models, where basically, we discussed all the way in the bottom, the equivalent circuit models. But really, you can write equations for what's happening in the diffusion in the particle all the way on the top. And you can also have reduced order models with something in between that actually it's what we call the single particle model. Just to give you an idea of of how it looks like. Not that I will go through it, but I do want to impress you. Okay, so this is actually a really fantastic graphic from our Control System magazine. You can see 2010. So it's a very nice article, and I'm using this graphic because it's just really, really, it says the story. So what you have in the beginning is you have this, the lithium, it leaves the particle that's shown in the blue, the circle, the sphere at the bottom that's shown as blue. The lithium leaves the particle, and actually it travels, it kind of swims inside the electrolyte. And then it actually crosses the separator as it kind of swims through the electrolyte, gets diluted inside the electrolyte, and then it goes to the other particle on the anode side. Well, so we can write actually equations that define the species concentrations in the two particles. That's the first equation. And it's partial differential equation in actually 2 dimensions. And then you can actually write, or actually the second equation, the first equation is the actual concentration of the lithium in the electrolyte, that fluid that actually carries the electrolyte. And then we have equations that define the charge balance, because it has to be balanced across this whole space. And then you have many equations, algebraically connected equations that connect algebraically actually both boundary conditions and also some of these parameters. So it is a very tough problem. Sometimes we actually do, well, we do a lot of simplifications very often by, let's say, neglecting the electrolyte. And in the single particle model, what we do is we say the electrolyte is not going to be so important. And so what we're doing is we are actually just estimating the 2 jars filling up and emptying like this. But as this graph to your left shows, it's not like that. It actually, as you empty the 1 jar and you put lithium on the other side, you create a wave, right? So it's the diffusion dynamics. And you have this pretty sharp, as you can see, showing with high current, you have this red line that corresponds here. And so you have high gradients in the concentration of lithium across the cathode. This can be damaging, because if you only, if in your model and what you're estimating is the average, obviously you are ignoring the extremes, and these are the extremes that are actually going to drive some of your part of your material into that dangerous zone that there'll be plating and dendrites. So, and this is what this graph shows. For example, if this is a really aggressive cycle, it's actually, I have, well, the privilege to work in a center that actually is funded by the Army. So this is driving a very large vehicle that it's armored, and so the current is really high. The 50 here is Cs, so actually the amperage is like close to 400 amps. So when you drive, you take this current out of these batteries, then you can actually, if you just were ignoring the electrolyte, you will have the blue line that shows in the lower graph. But what's really happening inside the electrode is the red line. And the red line can very easily go into the damaging zones and actually create a lot of problems. So the idea is to, when we saw all this, and again, it's really nice. I have a lot of students. My students are taking courses from reaction engineering and electrochemists, and so they actually know much more than me about the actual physics and what's happening. And they tell me about all these phenomena that can happen, and they try to actually include them in the models. And what you see to the left is all the things we worry about. So electrolyte oxidation and reduction. When the potential increases, then actually the electrolyte will oxidize. And that's when it oxidizes, like actually it's combustion inside the cell. You will have these lithium dendrites, basically these big strikes. These are the dendrites that are growing through, and they can sort the cell. We have electrode stress and cracking here. It's shown very nicely in this picture. So what it's doing when it's cracking, it actually can disconnect the particles, and your resistance can increase. But also it can eat up more lithium and then put it in a place that you cannot move it anymore. So you lose lithium. That's why your capacity degrades over time. And then, of course, you have some defects, and then the huge problem of thermal runaway. If your temperature increases above a value, then you have oxidation, and the reaction completely shifts to a very fast dynamics, very thermal, exothermic reaction, and you can't actually even stop it. You don't have so much cooling anymore. Okay, so these are happening inside the cell, and this is only what we monitor. We can monitor voltage, perhaps temperature on the surface of the cell, and we know the current we're drawing from it. And this is what we control. We can only deny current, and we can control perhaps the coolant flow rate and the temperature. So we are pretty limited in what we do. I call it actually driving blind. Of course, estimation is helping us drive, well, less blind, but depends on the model. So some of us actually, we really wanted to understand what's really happening and actually validate some of our models. We even wanted to know the limitations. What is the range that our models are going to be accurate so that we can use it, right? Can we actually even know the range of accuracy of our models? So some really amazing students, they said, hey, professor, you know, we can actually check this out. We can actually do an experiment that we can see inside the battery. So I call it the lithium goggles. So it's actually neutron imaging, and we went to nuclear reactor. So this is at National Institute of Standards and Technology at NIST. This is a 20 megawatt continuous power reactor. And what in this reactor is happening is they have these beams, and you take the neutron, and it's collimated in nice energy, and then basically this beam is shooting through your battery, and you can actually see the issue is that with the neutrons is almost the inverse of an X-ray. So the neutron goes through all the material like the copper and the aluminum, all the metal, but it actually gets scattered by lithium and hydrogen. The light elements are the ones that they stop the neutron. So that's why I call it the inverse of an X-ray. So what we can actually see is in real time the lithium from the anode to the cathode, how it transfers and where it is, and we can even see the concentration, the gradients that they could be damaging. We need a really good detector, and we need, of course, a very good system. You can see here Xin-Fan Lin. He was, this is actually, we put the battery in front of the beam. Xin-Fan runs away when the beam is on, and he goes and he sits outside this bunker, and we all out in the back. And what we see is typically this. So what you see here is our little battery. It's a very small battery. Let's see if I can do this. So it's mounted on an aluminum, solid, let's say, post. And then we are beaming this direction, vertical. And so what you see here in this 10 layers is actually the foils. Remember the toilet paper I was telling you in the beginning? Okay, so you have actually 10 folds. And you will be seeing actually how the lithium moves from each one of these folds from the anode to the cathode. In the middle graph here, it shows it's the raw transmission, so you see the intensity. Whenever it's dark, it's a lot of lithium because it gets blocked. And whenever it's very light, it's actually aluminum, so it goes through, so you see a lot of light. And what we will see is as it charges and then discharges, and let me run it for you, now that you think you know. So you can see the lithium moves from these edges to the center. And then as it starts discharging, it will move from the center to the edges. So that's the cathode. And I can run it again. On the top, I'm graphing the intensity, and the dashed line is the fully discharged case so that you have a sense how the intensity changes. So when you see this, you'll say, yeah, I got it, but it's kind of hard to see. Of course, you have to model the imaging system, and you have to actually deconvolve the information to actually do any type of model validation. But sometimes whenever we do experiments, it's amazing actually. We go to do something and something completely new appears in front of us. So what we were actually seeing very clearly, the gradients, it was not so easy to see, but what we could see very clearly, perhaps you could see it now, is this movement. Do you see this movement? This is not a movement, it's not like it's shaking, and this movement of the system is very high in the beginning, and then it kind of slows down as it charges, and I can do again and again, very repeatable. All the layers were moving the same way. In fact, they were moving, the farthest they were from the fixed location. They were moving more, of course. And the movement was as much as 2% of the volume of the whole battery. So it's actually quite a lot. And for us, it was a huge annoying thing because we had to remove the movement in order to compare the charge and discharge intensity and find the gradients. So it was very annoying. We had to actually read papers about how wide is this movement. We actually even looked into the nuclear reactor because we thought that actually the actual reactor was moving because it gets cold, and as you put the rods in and out, maybe our beam was changing intensity. But it was not the case. So what we found out later is that something that is actually very well known in the Electrochemical Society, I should say in the materials science field, that lithium-ion batteries, as they charge, and as the lithium intercalates inside the layers of carbon, it actually swells. Kind of makes sense, right? You actually put material inside the crystal. And you can see in this graph up there on the right that you have completely delithiated carbon, and then you put some, and then you put every 2 layers, and every 1 layer, and every other layer. And it actually grows and expands. It's like breathing. So we said, wow, you know, we can actually measure this swelling because this swelling is actually completely related to the state of charge. It's how much lithium it has in there, it will actually swell. In addition, what we actually also saw in these experiments, and that's the graph on the lower side, it actually, and some of you might have seen it, you know, it used to be that we have these batteries in our cell phones that we could actually take out and see. If your cell phone was not holding charge, have you ever looked at your battery? It's swollen. It's like a pillow. So what we actually found indeed is that as we were losing capacity, it was a residual deformation and the battery was swelling. So not only we can use the swelling for state of charge, we can actually use the swelling for state of health. And the problem is that we knew kind of the theory on the materials and crystal level, but we needed to move all the way to a whole system that goes into a you know, constrained layer there, so it swells only where it's not constrained, and then we have to go into a big pack, and in the packs that you have in your car, they don't swell. You actually compress them, right? They don't change size in your car. What you do is you actually constrain them, so what is going on is it's feeling a lot of stress as it's trying to compress. To expand, you're compressing it. So the strain is actually what cracks the particles, and that's what creates also degradation. So, okay, so it was worth the effort, however, because we still need a lot of this information. We actually said, yeah, we can actually get some estimation, better estimation, and they believed us. They gave us funding from Department of Energy and what we call ARPA-E, which is Energy Funding Agency. And because we, you know, don't typically carry neutron imaging in our devices, we worked with General Electric and Amphenol, and they developed this nice thin film sensors that they actually can measure strain, or they are pressure sensitive so that they can measure the pressure if it's under stress. We said, okay, we will put these sensors on the large arrays, on the cells. This way we will validate our models and the swelling characteristics, and then we will also do observability or sensor location analysis so that we don't put too many. We put them just right at the right place to get all the information, and it's at lower cost. And then we can actually try to see if we can make a difference in a very large pack. And Ford also agreed to actually test the algorithm and help us embed the sensors and the algorithms into their pack. We had a lot of fun. Ford gave us a whole pack. We had a disassembly party at the Auto Lab. A lot of people came over all the way from the mathematics department that they were doing how to fit as many cells as possible in a certain space, operational researchers, chemists, and of course mechanical engineers and electrical engineers. We had Ford engineers come and help us disassemble it. That's true, because this is high voltage, very quite dangerous levels, but we measured everything, we numbered everything. We were ready to do the modeling. And so here is the system where you see we have in an automotive pack, you have it under constraint. You don't let it swell. And so what we did is we actually took some cells and put them under the same kind of fixture, under the same compression. And then we embed the G sensors and got all the measurements we needed. And indeed, we could do what we call the fusion of the force and the voltage measurement for better state of charge estimation. And what is the point here again? Why is it better? If you have voltage, why would you add one more sensor and add cost and get state of charge? Well, again, perhaps there are some regions like this one here. Remember, the voltage is very flat. That's the voltage curve, the blue. And the red is the force as you change your state of charge. So as you can see, there are regions of state of charge where this alpha, the slope, is steeper. So you can get much better observability instead of nothing. And this is the statistics. The red is when you fuse the sensors, you get less variance at many state of charge, larger state of charge range. So that's good. As you can see here, we actually embedded the RTDs, and together with the strain, so that we can also measure temperature. And indeed, temperature also affects the swelling, right? When you take current out of a battery, you obviously are going to heat it up because you have I square R heat losses, right? And because you're going to heat it up, or in any case it will heat up, even if you're parked under the sun and it gets warmed up. The aluminum and the copper, as it increases temperature, it will actually expand. That's the classical thermal expansion. So this is the measurements, as you see, for different temperatures. You can see actually that for 10 degrees temperature change, the actual force you get is as much as the intercalation type of force. So you have to have a very good thermal characterization of your cell, that you know the thermal expansion, and you can disassociate that or exclude that when you come up with the intercalation type of expansion. So this leads us to multi-physics type of models and also thermal state estimation. Okay, in all honesty, I am motivating temperature here because I wanted to actually utilize strain and the expansion, but temperature is on its own very important, right? High temperature will actually, remember, cause oxidation of the electrolyte and actually thermal runaway and many other things. So you actually do want to have a temperature. If you have many cells in a pack that are in various temperature gradients, you will actually age them differently. So you have a big problem about cell-to-cell variability and many other things. So it's worth on its own. I just used this story to kind of motivate the multi-physics models and this estimation problem. And again, you have all kind of models, distributed parameter models, reduced models, and the simplistic models. So one simple model again, which is kind of an equivalent circuit model, is the one that tells you the rate of change of temperature in the core. So this is our cylindrical cell, as if the heat gets all dumped in the middle, in the core, and the heat is I square R. And then you have some losses through conduction, so some heat goes through this RC to the surface, and it hits the surface, and then it also, there's a convection, so when you have coolant. So very simple two-state model. You can see that it's actually linear. It has, I can write it in this form, okay, continuous, discrete, it doesn't matter. And you have basically 4 parameters, and you can see that you have the regressors there, so you can actually estimate these parameters and then go back to the original physical parameters. So you can apply current excitation, flow rate excitation, so you can change your coolant. And if you do these 2 things, then you get your thermocouple just by measuring temperature at the surface of the battery. You can actually estimate all 4 parameters, okay? Oh, by the way, just to make it a little bit more interesting in case you are running out of energy. So if you have a, think about it, this is, look at the temperature curve here. It started at 25 degrees and it went really quickly to 45 degrees. This is at the surface, 40 degrees at the surface. The core will be hotter, right? And this is within something like 30 minutes. So next time, if you do a fast charging in your Tesla, and it's in a very hot environment, this is the temperature rise that you will see. So actually fast charging right now for electric vehicles, it is still a limit, and the thermal limit is still very important. Okay, so with this excitation, the point that I'm trying to make is that you can actually, with this simple model, you can estimate all your parameters. Once you have the parameters, you can also use this model to estimate the core temperature, because it's actually the hotter spot, and you want to actually save and be careful so that you don't exceed the temperatures at the core. Again, the classical thing, we have our model, we estimate the surface temperature, we compare it with the measured surface temperature, we create an error, the error will make our estimation converts faster, and we can also do the parametric estimation. Here is some experiments. The black line corresponds to the actual core temperature, and the red line corresponds to the estimation when we actually include that output feedback, whereas the red line here corresponds to the core estimation if you did not have the closed loop feedback, the estimation error. This is important. I come from the United States. The Department of Energy is funding millions every year on models, but they still don't have the notion of output and feedback estimation for some of these models. They just have models by themselves. They say if the models are accurate, we can actually have a supercomputer in the car, don't worry, cloud computing, and we can estimate everything. They still have not merged the models with the sensors. So I think there is a lot to be done from our field to actually get all these nice models that they're developing to improve them, and doing it, it's going to be really satisfying. Some of you might be thinking, how do I actually know the core temperature? And how do I know I get to the right value? And achieve this 15 minutes faster convergence rate? I actually had another amazing student who says, Professor, I really want to test that, and drill the battery and install the thermocouple. Please don't drill the battery by yourself. You have to do it inside an argon glove box. And then get through a lot of sequence of choosing the right epoxies and to seal it and get it out. But having, again, this fantastic students, you can do a lot of, really dangerous stuff. You can do, using this parameter estimation, you can also do a lot of aging. These parameters, if your resistance is increasing, then you know you are aging, so it's a state of health. If your heat transfer coefficient is decreasing, then you know something is wrong, and it could be a coolant fault. So this way you can use it actually for fault detection. You can take this model and propagate it to a pack, because unfortunately we don't put a thermocouple or an RTD on top of every cell. In packs in the vehicle, you have hundreds of cells. Right? I guess the Tesla Roadster has how many? 7,000 of these little guys. So how do you actually place the sensors in the few cells to actually be able to get the information you need for all the cells and also for the core temperature of the cells? That's very simple. You add cell-to-cell conduction and airflow heating, so it's all manageable, to be honest. There is a lot of work to be done in our field with a lot of fundamental work that has been done already that needs to be transferred in batteries. So far, we used, myself, my group, a very simple observability criterion in where to place the sensors. Some other work by Professor Kristek and Mora, they worked with the exact PDE. But as I said, there is a lot of work to be done. To be honest, if you go by observability, the answer will be, oh, you need 24 sensors in a pack of 120 cells. And the automotive manufacturer will tell you, you must be crazy, get out of here. Why? Because they're using only 2 or 4. So what we need to solve is this last line I have there is the kind of constraint, so optimizing the observability under a constrained number of temperature sensors, because the automotive manufacturers will not put more than 4 or 5 or at max 6. And you have to really quantify the cost benefit, the cost ratio effectiveness for that. Propagating this in prismatic cells, everything I've shown you is cylindrical cells, so the model is kind of easier. It is doable. Here, just to give you a highlight, we propagated in a big pack with 76 cells with Ford, and that's 2 degrees errors in a 35 Celsius operating range for 76 cells. And I think, yeah. So these are the sensors. Maybe you don't see them. They're sticking out here. And we use these 2 sensors for the measurements and some other sensors for the validation. And what do we gain? Again, as I said, whenever you put sensors and you do estimation, the problem in our field is that we are doing it to be safe, to be robust. And the problem is that the automotive manufacturers want to also see the cost benefit. So what we try to do is take it a little bit a step further and say, okay, if we have this estimation, fast estimation, and a good prediction, we can actually be more at the edge, be more risky, and actually use more of these batteries and get away from all these big thresholds, all these big safety margins that they include. So this is a simulation. And it shows, so let's see, it's versus time. The x-axis is seconds. The black line corresponds to demanded power. So this is the power that we want to draw out of the pack. This power, sometimes you will not draw it because the BMS will say, nope, you can't do it. And these are the lines here. The conventional power limits is the blue lines on top and bottom. Whenever the black exceeds the blue lines, it's like a power denial. No, you can't draw this power. You better go to an engine or something else. And then what we did is we actually developed the dynamic power limits based on our models and prediction, which you can see are the red lines, that they are bigger than the blue lines, bigger, so we're more aggressive. And we can draw more power. You can see in the beginning, we actually violate voltage constraints. So down here, it's the voltage constraint, but our algorithm actually allowed to use much more current than the blue line. And that's because the temperature is cold. This was operating at -5 Celsius, simulated at -5 Celsius. And at 5 Celsius, the battery cannot give you actually, the resistance is very high. And so it hits the low voltage limit. Still, we did better, and because we allowed to take more current without violating constraints, we heat up the battery faster. So you can see that the blue, which was the, let's say, conventional power limit, was slower to increase its temperature. Well, obviously, if you don't drive your cell harder, you're not going to heat it up faster. And if you're not heating it up, you're not going to be using it a lot. And so it's also fuel efficiency and drivability. And then you see that there were occasions that we were actually more conservative than the conventional case, and that is because we were driving our cell to lower limits. This is 20% SOC, so we were almost depleting the cell. This was a hybrid application that typically they operate at 50%, and we drove the cell down to 20 because we said, no, it's okay, we can do it. Our estimation is very good, so it's okay to be down to 20. And then when we saw this in simulations again, Ford actually took the challenge and said, yeah, we will actually show this in a pack. So this is in a Ford pack. This is a full hybrid, the hybrid pack that you would have in a C-Max or a Fusion vehicle. And I call it the octopus pack because of because I'm Greek, no. Because of the cooling pipes. So it's inside an environmental chamber, so it keeps -5 Celsius all the time, what we call the winter cycle. And it operates at 30% SOC, so it's a depleted level to make sure that we challenge our estimation. And these are now data from the pack, and you can see the red lines correspond to the Ford limits. These are Ford limits. I don't know what they are, but they're very close to what I called earlier conventional. And the blue, the black is actually ours. Sorry, the black is the Ford and the red is ours because it's wider. Okay, again, fast warm up and probably same or less degradation because we are operating at low state of charge, so it's less strain. At the end, we can actually use the other, so we had a same pack and we can draw 25% more power from it. But maybe, you know, that would be for a sports car, but maybe what we can do is the other way around. If we can draw more power, we can downsize the pack for the same power and have less cells, and so this way we can improve the cost. So indeed, we can actually reduce the cells by 21%, have faster warm-up by 1.5 minutes, so that will affect fuel efficiency, et cetera, you know, all good. Otherwise, I wouldn't be showing that to you. And I'm approaching, you know, my last few slides, which are things that I'm doing currently. So there's a lot of work and a lot of need in the area of fast warm-up in sub-zero temperatures. Right now, packs, at least in automotive area, but also energy storage area, the limitations are during low temperatures. Low temperatures, batteries cannot be very fast in providing power, but they can also be very dangerous in accepting power. You can't charge them. So if you had a nice, fantastic Bolt or a vehicle that it's all electric and you want to charge it fast, but it was cold, you have to wait first to warm it up before you charge it. So I'm actually not going to spill the beans. This is a paper that I will be presenting this afternoon. Sorry about the advertisement. And it's a very nice way. We turned it into a reachability problem study. Some things that are actually out there, and again, having brave students help. They keep me away from the lab. We actually trying to understand right now what's going on in internal sorts. Depending on what layer is sorting, you can have completely different behavior. If you're sorting in between two layers like the B characteristic, shown in the red spot, then you can have the lower event where you're just rupturing the cell, you're swelling, you're rupturing the cell, but you only have smoke coming out. So it's okay. If you had good ventilation, it's fine. But if you had another sort, like the one that goes all the way to the D or the A, then you actually have blasting, burning metal when it ruptures. So trying to understand what is a sort and which one is the dangerous sort is very important for us. And the point that we're trying to make is not just to understand it, but to also have an early detection. So this is the idea of putting the sensors, as you can see here in a cell, and trying to see, this is the graph that it's really fantastic, and I think it's really worth my last 2 minutes showing you this. So this is